Okay, so today I'm going to present you my paper on flexible task graph representation and its generation from C applications. Open parentheses, work in progress. So I think we are all more or less familiarized with the concept of taking an hardware accelerator in order to improve the performance of a generic application. So I have an application that is running on the CPU, and I will try to find performance critical sections or regions in that application and offload them onto an accelerator to improve its execution time, energy consumption, and so on. And of particular interest to us are FPGAs, because they are very adaptable and can pretty much try to extract as much performance from almost any arbitrary piece of C code that you can think of. But the problem is that this mapping and trying to find these regions is yet a fairly unsolved problem. And typically, in order for us to find these regions, we need to model the application as a task graph. So what is a task graph? There are many definitions, but in essence, it is a set of tasks, so units of computation, and their relationship, which is usually in terms of data communication and data dependencies. And task graphs are usually built after a type of application. So for instance, if I have, say, something like a neural network, where I have function calls that implement each layer, then my task graph is probably going to represent the layers of the neural network. The problem kind of starts to arise once you want to generate task graphs from generic applications. You can't make any assumption about the organization of the application, its architecture, or anything like that. And so having a task graph where each task maps very cleanly into one syntactic feature, like a function, a statement, a loop, is very, very hard. And the other issue as well is that the problem of trying to decide whether a task stays in the CPU or is offloaded is also NP complete, because the more tasks you have, it starts growing quite exponentially. This problem is further worsened once you start to consider regions that go beyond these typical syntactical features. So for instance, imagine that I know a priori that the best region for offloading is a region that shares data with that variable called filter, which is a buffer. So I have a function, then I have a couple of statements, and then I have another function. How do I generate a task graph that can capture all of these different structures and actually tell me that these are the tasks that are of interest to us and nothing else? And furthermore, how can I do this while preserving the original source code? So this would be very easy if I lowered this down to, say, LLVM or some other intermediate representation, but I want to keep the original source code because I want to generate HDL from it or target a GPU or something like that. And for this purpose, we propose what we call the extended task graph. So the extended task graph is an AST-based representation. So it uses the AST representation of the source code and doesn't break that source code. It preserves its readability, its retargetability, so everything you do on the task graph is almost innocuous, because whatever you do after is perfectly possible. And we want also to enable flexible task granularity. So our tasks no longer map to one specific syntactic features. We can actually take a task, divide it into smaller tasks, increasing the granularity, or join two or more tasks together into a larger task. And of course, we also want to make data communication between tasks very, very clear, so that we know what the lifetime of the data that is shared between tasks is clear for us, because we may be very interested in selecting groups of tasks or clusters that share the same data, which is very important when you want to create efficient FPGA accelerators. And so in order for this task graph representation to be possible, we first need to convert our source code into what we call a normalized C code representation. So we take input C code, which can be written in any style with many different kinds of syntactic features, and we will, through source-to-source code transformations, reduce it down into this format. So our code only has functions, and every function is one of two types. So the first type are functions that only have pure computations. No side effects, no calls to other functions, no funny business with global variables, or anything like that. And the other type are functions that only call other functions. We have also very basic control, so like if statements and for loops with a single level, so no nesting. But through extensive code restructuring, we can get an easy application within reason to map into these two types of functions. And so now that we have settled on a standardized representation of C code that we can work with, we can actually start to define the extended task graph. So in essence, our standard task graph is a directed acyclical multi-graph, where each node can either be a task by itself, or it can be a cluster of tasks. So basically, we have graphs inside graphs inside graphs. And the edges represent the communication of data from one task onto the other. And as I said before, the extended task graph is an overlay of the program's AST. So everything we perform on the task graph is reflected on the AST and is always kept correct. So whatever we do on the graph will be reflected on the AST, and we can then generate code according to that. So if I have a function called F1, that will be my starting task, let's call it that. And then I have a call to F2, which is going to be mapped into its own task, F2. Then I have a loop with F3 and F4, and since F3 and F4 don't share data, don't have data dependencies, they can be each offloaded onto their own separate tasks, each with the 100 iterations each. The same cannot be said for this one, because F5 and F6 have data dependencies. So we will create a task for the loop in general with those 500 iterations. And then inside the loop, on a lower level of granularity, we will create the tasks. And then just another one for good measure. So in essence, all the transformations that we do on the graph will be reflected on the ST. So merging tasks is function inlining, and splitting tasks is function outlining. Furthermore, about data communication. Data communication is always done on the data item level. So a data item is basically a discrete piece of data with one or more names. So that one over there, filter, will always have a single path, which is called the read-write data path, which is a path that shows me where the data is modified, and it is always linear. But it can have a few spurs that represent tasks that only read that data and don't modify it. Yet again, about the changes in granularity. So imagine, for instance, that I have that very sequential, very small task graph, and I want to extract some parallelism. So I can take task T2 and split it into 3 separate tasks, T2A, T2B, and T2C. And what that is, which leads to more task level parallelism, because I now have 3 tasks that can execute in parallel. And the matching operation in the AST will be that I will take those 3 statements and basically outline them into their own functions. This is a very basic example, just one statement. Of course, in a real scenario, this can be arbitrarily complex, multiple loops, multiple functions, whatever you want. So, in order to kind of see how this task graph behaves using real-world data, we used some benchmarks from the Rosetta and the MachSuite benchmark suites, and we generated the task graphs. And we see that around, we never have more than 20-something tasks per graph, which is an interesting number because it allows us to both increase the granularity of a task graph, increase the number of tasks a little bit more, because our problem with the exponentiality is still quite manageable at this point, or also to decrease the granularity and create smaller graphs. Then, about those read-write paths and read-only paths that I mentioned, we also took for each data item an average of their typical length, and we see that most data items only survive for about 2 tasks. So the lifetime of our data items in these benchmarks tends to be very small, which can then also further inform us about the kind of clusters that we can create around tasks that use the same data. Then, about the level of parallelism, so we gathered every subgraph in the task graphs and calculated a measure of parallelism, so basically the critical path divided by the total number of tasks in that task graph. And you see that for the most part, we have always a round of 2, which means that about half of the tasks can be parallelized out of the box. But there are still a few examples like that one with 1 that could maybe be a very interesting case where we could pick it and try to split the tasks, increase the granularity in order to extract more parallelism, because as it stands, it has none. And finally, also very important in the context of FPGAs is the percentage of total communication that is done through a producer-consumer relationship. So one task produces the data, the other one consumes it, and this is done linearly, which can lead to the creation of a dataflow region, which can be very easily exploited by an FPGA. So finally, almost to conclude, let's talk about a little bit about the tool flow. This is implemented with Java, a source-to-source compiler, C++ and C++. It's the same as the one used in the Rust borrow checker that you saw 2 presentations ago. And basically, all that I've mentioned here is completely automated. So we have our code transformations, our task graph generation, our metrics and properties extraction, and in the future, also an actual partitioning engine that will create these code regions and therefore them into the FPGA. And then, of course, output the host C code and the accelerator C code already separated and ready to go. And so just to wrap everything around, we talked about the problem of offloading an arbitrary application into an FPGA. We talked a little bit about the C standard that we need to have in order for us to do this. We talked about our extended task graph representation and a few properties that we extracted from it that will inform our future research. And that future research is exactly to perform a method that partitions and optimizes the code by doing a single pass over the extended task graph. And that is all. Thank you for listening. Okay, so in essence, that's still our current work. That's where we want to get to. This is just the representation that will allow us to actually export that. But ideally, we want to come up with an heuristic method that tries to balance in one way tasks that share the same data, the physical constraints of the FPGA, like the number of resources, and also the parallelism that is inherent within a cluster of tasks, which can or not be exported by the FPGA. So trying to come up with this, let's call it this magical formula, is basically the whole point of my PhD, which is still very much early days in regards to that. But this representation is already built with all of the information that we need in order for us to be able to reach that point someday. Yeah, so we made some experiments with this, with actually some motivating examples where I did this by hand. And in fact, we did find that FPGAs, in the data center type, like when you have one of those PCIe accelerators running on data center, in fact, there is nothing much to gain when compared to the CPU of those machines. But once you get down to the embedded, where you have like a small, low-powered ARM CPU and a modest FPGA, things are much more balanced, and there's much more we can actually gain by doing this right. So a naive approach that would just select the kernel and what it run would still probably not be good enough, but by selecting regions that are a little bit more interesting, we can actually extract more than just running it on the CPU.